One of the biggest stars we've ever found is wobbling on the edge of disaster. And it won't go quietly. It might collapse in on itself and instantly become a black hole, or explode in a blinding supernova. It might even crash into its companion star, and we could probably see it. The star in question, WOH G64, wow, that's a mouthful, I'll nickname it Jerry. So Jerry is a red supergiant. These are huge stars at the end of their lives. Like cosmic seniors, they've already burned through most of their fuel, puffed up to an enormous size, and are getting ready to explode as a supernova. They're cooler on the outside than many other big stars, that's why they glow red instead of blue or white. Still, the biggest and brightest of these stars are kind of a mystery. Astronomers aren't totally sure what happens to the most extreme ones right before they explode. When they look at the sky, they don't see as many ultra-bright red supergiants blowing up as they would like to. Instead, they see hints that some of them might change color and heat up again before the end. One famous example is our star called WOH G64 in the Large Magellanic Cloud. That region is basically a stellar nursery. It means it's packed with thick clouds of gas and dust where stars are born. It's the perfect place to grow something extreme. Now, for decades, we considered Jerry one of the most outstanding red supergiants ever found. It's enormous, it's incredibly bright, like me, and losing mass like crazy. It's also surrounded by so much dust that it looks heavily wrapped up, like it's hiding inside a thick cosmic blanket. But recently, something weird happened. The star's light signature started to look completely different, as if this red supergiant had changed identity. Now scientists think Jerry isn't just a single star. It's probably a rare pair of stars locked together in a relationship called a symbiotic binary system. In this system, the red supergiant seems to have transformed into something hotter and more unstable, called a yellow hypergiant. Now, yellow hypergiants are like the middle phase before total destruction. They're enormous. Some are so big you could fit billions of suns inside them. But they don't last long. This stage is brief and chaotic, like a star pacing nervously before its final act. Yellow hypergiants are extremely rare because they represent a short transition between the red supergiant phase and the final explosion. We know of only a few dozen confirmed examples. Now, why would that transition happen? One possibility is stellar drama. Ooh, what could happen? Well, as we know, Jerry isn't alone. It likely has a companion star. The two may have interacted so intensely that the red supergiant blew off a huge chunk of its outer layers. Imagine two stars spinning around each other so tightly that one basically starts stealing material from the other. That lost material could have formed a massive cloud, a shared envelope that briefly swallowed both stars. But there's another possibility. Even without interference from a companion, a star this massive can become unstable on its own. It might have gone through a huge eruption that lasted more than 30 years, and is now settling down into a hotter yellow phase. Whatever it is, this is incredibly rare, like watching a star evolve in real time instead of over millions of years. In any case, after watching this monster star suddenly change before their eyes, astronomers now think it may be getting close to the end. A new study claims the star could be on the verge of exploding in a massive supernova. Or, since it's so unbelievably heavy, it might skip this step completely and collapse straight into a black hole. Now, Jerry was discovered about 50 years ago and labeled a red supergiant. It has about 30 times the mass of our Sun. But the really mind-blowing part is its size. If you drop this star into the middle of our solar system, it would stretch all the way past Jupiter. Stars like this live fast but not long. Jerry is only about 5 million years old. That might sound ancient until you remember our Sun is 4.6 billion years old and still going. The problem is, massive stars burn through their fuel super fast. That's why they shine so bright, grow to ridiculous sizes, and then go out in a blaze of glory. Now, we don't know how it'll happen, but because of its enormous mass, Jerry's demise won't be quiet. In cosmic terms, it could happen soon, meaning within a few hundred to a few thousand years. It might explode in a supernova, blasting its outer layers into space. Or it could collapse inward so violently that it forms a black hole on the spot. There's even a chance it could eventually slam into its companion star. So let's say our red supergiant tears itself apart in a supernova. Then we need to learn more about these space fire shows. Supernovas are gigantic explosions that happen when massive stars finally collapse. They're incredibly important to how we understand the universe. Astronomers use certain types of supernovas, like measuring sticks, to figure out how far away galaxies are. In fact, it was supernovas that tipped scientists off in 1998 that the universe wasn't just expanding, it was actually speeding up. But there's one problem. Even though supernovas are powerful and bright, they happen incredibly fast. Catching the exact moment a star explodes is like trying to photograph a lightning bolt at the exact second it strikes. But an international team of astronomers says they managed to do exactly that. They got the earliest and most detailed look ever at a supernova right as it was blowing apart. Using the European Southern Observatory's Very Large Telescope, they basically watched the shockwave from the collapsing star blast through its surface. For the first time ever, they could actually see what shape the explosion had. And that shape does matter. When a massive star runs out of fuel, things go bad fast. For millions of years, the star balances two forces: the nuclear fusion in its core pushing outward, and gravity pulling inward. But once the fuel is gone, gravity wins instantly. The outer layers crash inward, slam into the collapsed core, and rebound outward in an intense shockwave. That shockwave tears through the star and blows it to pieces. The result is a supernova. That's the basic idea. The details of how that shockwave forms have been hard to pin down, because supernovas are nearly impossible to catch in the act. Out of the trillions of stars out there, astronomers would need to be already looking at the exact right star at the exact right moment. And it would have to be close enough to study before expanding gas clouds block the view. This time, they got lucky. The explosion happened about 22 million light-years away, which also means it happened 22 million years ago. Think about that. Astronomers spotted it quickly and managed to start observing it within just 26 hours after it was first detected. In supernova terms, that's incredibly fast. They used a technique called spectropolarimetry, basically a way of studying how light is scattered and how its vibrations are aligned to figure out the shape of the blast. What they found was surprising. The explosion wasn't perfectly round. Instead of expanding like a smooth sphere, the shockwave stretched out slightly, more like an olive than a ball. When the blast slammed into the gas surrounding the star, it flattened, but it still expanded evenly along that stretched shape. It means the very first light and material didn't shoot out evenly in all directions. The explosion had structure right from the start, and that structure gives clues about what was happening deep inside the star when it collapsed. Now, here's another interesting fact. The star that went supernova was a red supergiant, about 12 to 15 times the mass of our Sun. And based on how many red supergiants are out there, astronomers expected to see lots of them exploding. But for years, they didn't see many. It was almost like these giant stars were disappearing quietly. More recent observations from the James Webb Space Telescope suggest they probably are exploding. We just couldn't see them clearly before. Maybe because dust and gas were hiding the blasts. And now, this new observation suggests their explosion might actually follow a common pattern, with a clear stretched shape rather than a perfect sphere. In other words, these cosmic explosions may be more organized than we thought. Now, for years, planets with two suns felt like science fiction, something that only worked in Star Wars, with those famous double sunsets on Tatooine. But now, astronomers think those worlds may actually be real, and not just one or two of them. Scientists have found 27 possible planets orbiting two stars at the same time. Along the way, they also spotted some other Star Wars worlds, too. Some worlds in the saga seem too extreme, but space actually has planets like that. For example, There are worlds like Kepler 10b and Kepler 78b. These planets orbit so close to their stars that their surfaces are literally melted rock. They're not a bit warm, we're talking about lava oceans. The ground is constantly reshaping, the crust trying to form and instantly getting torn apart again. If you stood there, which you absolutely wouldn't survive, it would be like standing next to a furnace where the floor under your feet is boiling. Even the chemistry there gets interesting. Those places might be packed with heavy elements like iron, which means that, in theory, it's the kind of world a mining company would love. In practice, it would be like trying to mine inside an active volcano vent. This planet is just like Mustafar from Star Wars, the place where Anakin and Obi-Wan had a lava duel. Now let's visit another extreme world that basically looks like Hoth, a frozen, empty planet where there's nothing but snow, wind, and survival problems. In real life, we've found exoplanets that feel pretty close to that vibe too. One example is this distant world. It floats more than 20,000 light-years away. It orbits a dim red dwarf star, so it barely gets any heat at all. The result, well, isn't nice. Temperatures drop below about minus 370 degrees Fahrenheit. That's colder than most natural environments we know of. The planet is a frozen rock drifting in near darkness. So if Hoth had a real twin, this would be it. Then there's Bespin, the gas giant with floating cities like Cloud City. In Star Wars, it's kind of romantic. Giant clouds, platforms, a whole civilization living in the sky. In reality, gas giants are usually the complete opposite of friendly. Most are just huge balls of hydrogen and helium with no solid surface at all. But astronomers have found some that sit in a more interesting zone. One example is 47 Ursae Majoris b. It's a gas giant, but its orbit puts it in a range where temperatures could be around 41 degrees Fahrenheit. That's not even cold, it's just, cool. And if a planet like that had the necessary kind of atmosphere layers or floating structures, sky habitats wouldn't sound totally impossible. Not likely, but not pure sci-fi either. When you line all of this up, it gets kind of suspicious. Mustafar-style lava worlds are real. Hoth-style frozen wastelands exist too. Even Bespin-like gas giants can sit in comfortable temperature zones. So, what if Star Wars didn't just invent these environments, but borrowed them from real life? After all, some of those really existing worlds are too weird even for sci-fi, like circumbinary planets. Those are planets that orbit two stars at the same time. Astronomers have now confirmed more than 6,000 exoplanets. That's a huge number, but fewer than 20 of them are circumbinary. Imagine our Earth trying to circle two suns instead of one. The orbit would get very tricky very fast. This is probably why discoveries of such planets are so rare. Now, most planets are found using something called the transit method. It's quite simple. You watch a star, and if a planet crosses in front of it, the star gets a tiny bit dimmer. It's not a big blackout, more like someone briefly moving a coin across a distant flashlight. From that tiny dip in light, scientists can figure out size, orbit, and sometimes even what the planet is made of. But this method has one big issue. It only works if the planet's orbit lines up just right with our point of view. If the orbit is tilted or chaotic, which is common in binary systems, the planet might never cross the star from our angle, so we just won't see it. That's why binary star systems are tricky. That's not because they're rare. In fact, most stars in the universe probably live in systems with two or more stars. But planets in those systems tend to have unstable or complicated orbits, so detection gets even harder. And still, astronomers have managed to catch a few. One of the first big ones was Kepler 16b. It sits about 250 light-years away and is roughly the size and mass of Saturn. It orbits 2 stars instead of 1, but surprisingly, it does it in a stable way. The way this planet was discovered is kind of subtle. One of the scientists who worked on it explained that we had never actually seen the planet directly. We've only seen changes in brightness, tiny dips in the combined light of the system. Based on that pattern, scientists reconstructed what must be passing in front of the stars. There's also another detection trick for binary systems. Instead of just looking for dips in light, scientists now watch how the 2 stars move around each other. In a stable binary, their motion is predictable. But if something else, like a planet, is tugging on them, the rhythm gets off slightly. We can see small timing shifts and weird wobbles. That's a clue that something invisible is there. Researchers have recently tested this idea on data from nearly 1,600 binary systems with the help of NASA's TESS telescope. They found 27 systems that might contain planets, and more than half of the candidates were likely smaller than Jupiter. But these are still maybe detections. To confirm them, scientists need more data, like deeper light analysis and follow-up observations. Now, even experts are cautious here when scientists explain that a lot of our knowledge about exoplanets comes from the planets that are easiest for us to detect. In other words, we're not seeing a full picture of the universe, and there could be many more strange or hidden worlds out there that our current methods simply miss. Then there's another problem. Planets in binary systems might not survive long. Some studies suggest 2 main outcomes. Either the planet gets pulled too close to its parent stars and is torn apart by gravity, or it gets flung out of the system completely. In both cases, the planet is a goner. So, even if circumbinary planets are more common than we think, they might not stick around long enough for us to easily find them. That's why researchers are now trying new methods, because right now, the big issue is how many planets likely hide in plain sight, simply because our tools aren't designed to see them. But we can detect other cool planets orbiting single stars, and some might even be suitable for colonization, like a planet candidate called GJ887d. It's not too far from Earth, just 10.7 light-years away. Scientists call it a super-Earth because it's bigger than our planet and heavy enough to have strong gravity and a thick atmosphere. Another great thing is that its parent star doesn't flare up much. Big stellar flares can blast away a planet's atmosphere, so the fewer flares there are, the better chance a planet has of holding on to air, water, and maybe even life. Another potentially habitable exoplanet is Gliese 667cc. It's just 22 light-years from Earth. This planet is around 4 times as massive as ours, and completes one orbit around its host star within 28 days. In other words, a year on this Earth-like planet is 13 times shorter than a year on our planet. Luckily, the star is a cool red dwarf, so the exoplanet most likely lies in its habitable zone, an area around a star where a planet could have liquid water. But there's still a chance that this world might be regularly baked by the flares from its parent star. And that's the thing. The more planets we discover, the less our solar system looks normal. Worlds with lava oceans, twin suns, and giant storms may not be rare at all. And we've just started looking. The Earth, frozen and alone, exiled into deep space. Jupiter, the only remaining planet orbiting the Sun. No, it's not a premise for a disaster movie. It's one of many real scenarios scientists explored in their latest simulations. This time, the threat isn't the sun swelling or a giant asteroid knocking planets into it like a cosmic bowling ball. It's something quieter and possibly already on its way. A recent study examined the potential consequences of a passing star coming too close. One such flyby could send planets crashing, flinging them into space, or mess with their orbits just enough to cause climate changes. But what are passing stars, and how likely is that to occur? Passing stars are normal stars, like our Sun, that move around the Milky Way. Since everything in space is always moving, sometimes stars pass near each other. Usually it's not a big deal. But if a star gets really close, its gravity can tug on planets like Neptune. That tiny tug can slowly change how the planets move, like a ripple spreading through the whole system. Scientists study these close encounters because, even though they don't happen often, they can have big effects over millions of years. They help us understand shifts in planetary orbits and how they may have shaped Earth's past. In fact, one theory suggests that a flyby 56 million years ago is what caused great climate change when Earth's temperature rose by up to 14 degrees Fahrenheit in just a few 100,000 years. That huge temperature jump changed life on Earth, leading to the evolution of some species while causing others to disappear. Even though it's impossible to prove whether there was a flyby a long time ago, we do know that events like this could mess with Earth's orbit in the long run. That's in the past, but what about the future? So far, we know that the solar system will have a close encounter with another star called Gliese 710 in about 1.3 million years. Gliese is moving towards us and is projected to pass within 10,000 astronomical units of the Sun. It won't come close enough to throw planets off, but it could still send icy comets from the Oort cloud our way, like a bored kid tossing a snowball without looking. One might hit something, but probably won't. However, in a recent study, scientists wanted to explore a more extreme scenario. What if a star passed even closer, say just 100 astronomical units from the Sun? That's about 100 times the distance from Earth to the Sun. From our point of view, it's almost unimaginably far, but in space, it's practically brushing shoulders. They ran thousands of long-term simulations covering up to 5 billion years of our solar system's future, and it turns out it doesn't take much. Just one close encounter can be enough to disturb the outer planets, like Neptune, and set off a slow-motion chain reaction that ripples inward. Over time, that gentle nudge can throw the whole system into chaos, a true cosmic butterfly effect. The good news is that even in this worst-case scenario, in 95% of simulations, the passage is nothing to worry about, and all the planets remain in place. However, in the remaining 5%, well, it's one disaster after another. The most frequent casualty in these simulations was Mercury. In nearly half of all unstable scenarios, Mercury ends up on a doomed path straight into the Sun. It's the smallest planet and the closest to our star, so it's especially susceptible to gravitational nudges, whether from the gas giants or from a disturbance rippling inward from a stellar flyby. When Mercury spirals into the Sun, you might think it's game over for the rest of the planets, but that's not always the case. Sometimes the system absorbs the loss and restabilizes, like an orchestra that keeps playing even after one violinist falls off the stage. Oops. Funny enough, Mercury already has a chaotic orbit, the most stretched and tilted of all major planets, and some studies already consider its fall into the Sun in the distant future inevitable. Now, Venus has a slightly better chance in these chaotic scenarios. It doesn't get ejected or swallowed by the Sun as often as Mercury, but it's far from being safe. Most of the time, the instability happens after Mercury goes rogue and disrupts Venus's orbit, nudging it into a slow-motion crash course with Earth or Mars. Even without the interference from field stars, long-term simulations show a tiny but real chance that Venus could eventually collide with Earth just from the way Jupiter affects Mercury. A Venus-Earth collision would result in both planets being completely destroyed. Oh well. A similar fate awaits Mars. According to simulations, in about 0.3% of cases, it either gets flung out of the solar system or collides with another planet. Mars is smaller and lighter than Earth, with weaker gravity, which makes it easier to knock it off track. What's interesting is that even in some cases where Mars is lost, Earth often manages to stay in place. Jupiter happens to be the heavyweight champion of the solar system, the proud owner of its own cloudy belts. Thanks to its massive size and strong gravity, it acts like an anchor, keeping everything else in check. There are 392 scenarios out of 12,000 simulations where all but one planet vanished, with Jupiter being the last one standing. Its stabilizing influence helps prevent smaller planets from going off course, and in some cases, it even helps the system recover after a disruption. Saturn, while less massive, seems to be Jupiter's loyal partner. But models show that when Saturn shifts its orbit abruptly, it can send gravitational ripples, known as secular resonances, straight into the inner solar system, nudging the orbits of planets like Earth and Mars. Finally, the most vulnerable ones are Uranus and Neptune. Sitting at the edge of the solar system, they're the easiest to knock loose, and in many simulations, they get ejected entirely. That loss sends gravitational ripples inward, disturbing the rest of the planets over millions of years. Even a tiny shift by 0.1% in Neptune's orbital distance can throw the whole solar system out of sync. The balance of gravitational forces would shift, forcing Jupiter and Saturn to readjust, which would push the disturbance toward the inner planets, destabilizing everything. Which brings us to the big question: what about Earth? While most simulated models leave Earth untouched, about 0.2% of the simulations end with Earth either colliding with another planet, Venus, or being thrown into the Sun. Out of 12,000 simulations, in 23 of those, Earth ends up as the only one still orbiting. But that's only if we don't include the Moon in calculations. With the Moon included, Earth becomes harder to predict. Our satellite could crash into Earth, get ripped away by a passing star, or destabilize our orbit over millions of years. Once again, this is a worst-case scenario, and while the odds are really, really small, it's not impossible. So, with that in mind, let's entertain the idea and see what would happen to Earth if it were to end up exiled from the solar system. Earth would become what scientists call a rogue planet, drifting through interstellar space with no sun to anchor it. The surface would quickly freeze, with temperatures dropping to hundreds of degrees below zero. But surprisingly, life wouldn't vanish completely. Earth's core would stay hot for billions of years, powered by radioactive decay and leftover heat from its formation. That heat could keep underground pockets warm. Scientists believe that this is the case with icy moons like Europa or Enceladus. Life might cling on in different caves or buried oceans. It wouldn't be a thriving world, but it wouldn't be completely empty either, at least for a while. Just cold, quiet, and alone. A ghost of a once lively world. And somewhere out there, maybe another civilization will look up, spot a faint blue dot drifting by, and curiously start running simulations of what might happen if this blue planet were to get really close, say just 100 AU from their sun.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Betelgeuse, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Betelgeuse. It's one of the brightest stars we can see from Earth. And it's just 640 light-years away. No big deal. Betelgeuse has a blue-white O-type star, which is one of the hottest types to exist. Betelgeuse was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Betelgeuse. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Betelgeuse replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Betelgeuse spinning way faster than it should for a star of its size. Huge stars like Betelgeuse are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Betelgeuse's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our Sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the Sun, but Earth's entire orbit around the Sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Betelgeuse might have less than 300 years of fuel left in its core. They say that Betelgeuse is known to expand and contract regularly, and its pulsation pattern hints that Betelgeuse is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VYCMA in our galaxy is thought to be closer to going supernova than Betelgeuse, and it's been dimming steadily over the past century, unlike the relatively stable Betelgeuse. If Betelgeuse was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Betelgeuse as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Betelgeuse won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.
Imagine you're looking up at the sky on a clear night, and you see all those beautiful stars twinkling up there. Well, one of them is Betelgeuse, a celebrity among stars. If you want to catch a glimpse of it, look up at the Orion constellation. It low-key looks like an archer holding a bow, and you can spot Betelgeuse as the reddish-orange dot on their shoulder. It's one of the brightest stars in the sky, so it's hard to miss. Betelgeuse is not your ordinary star. First of all, it's gigantic, up to 1,000 times the size of our sun. Can you imagine that? It's so enormous that if we could somehow replace our sun with Betelgeuse, it would engulf all the inner planets, including Earth. And here's another fun fact. When we look at Betelgeuse, we're actually looking back in time.
Yep, you heard it right.
Betelgeuse is about 600 light-years away from us, so the light we see today actually left the star 600 years ago.
It has quite a history. This star has been shining brightly for millions of years. Long, long ago, even before smartphones and telescopes, ancient Sumerians were the first to spot Betelgeuse in the sky, and it's been a diva this entire time. For example, in 1866, Betelgeuse became one of the brightest stars in the night sky. It was so dazzling that people could see it even during the day. Astronomers all around the world went bananas documenting this extraordinary event. Since then, Betelgeuse has been playing hide-and-seek with us. It all started when Betelgeuse started to dim back in 2019. Since then, it likes to dim and brighten sporadically. But these changes in brightness tell us about something important. As we mentioned, Betelgeuse was always a bit of a troublemaker. It's been living a fast and furious life. Because of that, it has been burning its fuel at an incredibly fast rate. The changes in the star's brightness are clues that Betelgeuse is approaching the end of its life cycle. The drama intensified when the Hubble Space Telescope snapped jaw-dropping images of Betelgeuse, like it was getting ready to blow its top. All this made scientists think that the star is close to retiring in a dramatic way. It's about to go supernova. So picture a star partying hard, powered by the fusion of hydrogen atoms. It's like the star's own energy drink, but just like any party, the fuel starts to run out. That's when things get interesting. As the star guzzles up its hydrogen fuel, it slowly begins to run on empty. It can't sustain itself anymore. So now, it's time for the grand finale. This finale is called supernova. The star collapses in on itself like a deflating balloon. The pressure and temperature inside skyrocket to mind-boggling levels, and this celestial tantrum triggers a colossal bang. So you can see why observing Betelgeuse is like having a front-row seat to the spectacular drama. But here's the big question. When will this happen? Well, the answer is not as simple as setting a timer. You see, stars have their own schedules, and Betelgeuse is no different. It could be tomorrow, or it could be thousands of years from now. Scientists have come up with only a rough estimate. They believe that Betelgeuse will go supernova within the next 100,000 years. Quite a spread, huh? Sure, that sounds like forever to us, tiny humans. But in the vastness of the universe, it's just a blink of an eye. But there's a chance, just a tiny chance, that Betelgeuse could surprise us all and go supernova much sooner. Considering its dips in brightness, we might be in for a show within the next few hundred years. We'll just have to wait and see. Now, if Betelgeuse does go kaboom, what will happen? Well, get ready for a show like no other, folks. When a star collapses under its own weight, it unleashes a cosmic firework of epic proportions. The star releases a crazy amount of energy in the form of light and heat. Betelgeuse's supernova is going to be extra special. It's like the superstar of supernovas. It will shine so brightly that it might even outshine the other stars in the sky. Picture that, Betelgeuse stealing the spotlight. The show could be so bright that you won't need a telescope to catch a glimpse. Nope, you'll be able to see it with a naked eye. It might even be visible during the day, making the sky look like it's hosting the coolest rave ever. After that, the supernova will keep us entertained for weeks. It will be like having a second moon in the sky, shining as bright as the full thing. Imagine that, 2 moons dancing together in the night. After several weeks of lighting up the night sky, Betelgeuse's supernova will slowly fade away, but it would leave behind a souvenir, an ethereal remnant. It's like a fading memory of the star's epic performance. This remnant, too, would slowly fade away over the course of several months. But it's not just about the light show. The boom will send out powerful shockwaves, and we might actually feel them right here on Earth. It's like the universe giving us a gentle tap on the shoulder, saying, hey, look at this amazing spectacle. How dangerous will it be for us? Well, we know that Betelgeuse's supernova would send dust and gas shooting into the atmosphere. It's like a big space sneeze. And this sneeze could cause a decrease in global temperatures. We're talking serious climate impact here. It could even lead to a mini ice age. But these are just assumptions. We don't know for sure if the consequences will really be that serious. But, of course, we want to be prepared for this event just in case. That's why scientists are studying Betelgeuse closely. But, in addition to serious scientific research, astronomers also have a blast of celestial comedy. Jokes are flying left and right. Someone has even created a Betelgeuse status account, which you can check yourself. So, as you can see, the star is keeping us on our toes. Astronomers keep observing it, and they need our help too. They want us to keep an eye on Betelgeuse and report any changes we see. How do you do that? First off, channel your inner astronomer and observe Betelgeuse. Take a peek at the star and note down what you see. Is it twinkling, shining, or feeling a bit dim? Jot it all down. Then be a superstar yourself and report your observations to the astronomers. Your observations will help them track Betelgeuse's journey towards its big supernova moment. You can also join in on some citizen science projects. They're super fun and easy, trust me. One cool project you can jump into is the Betelgeuse Brightness Monitor. By participating, you help scientists keep tabs on how bright Betelgeuse is shining. Your contribution can make a real difference. So join the monitoring team. You'll be part of something amazing, and who knows, your observations might even help predict when Betelgeuse will show off its supernova magic. By doing that, we can assist them in monitoring this superstar and learn more about the fascinating world of stars. But that's how we can help scientists to predict this event. Now, how can you personally prepare for it? First things first, you'll need the right gear to catch all the supernova action. A trusty telescope is like your front row ticket to the starry show. It'll bring you up close and personal with Betelgeuse's performance. And remember, you'll need special eyewear to shield your eyes from the intense burst of light. Safety first. And of course, prepare in case it decides to mess with our climate. Stock up on essentials, like warm clothes and supplies, just in case we experience a mini ice age. But let's just hope it won't happen. So keep your eyes on the night sky, my friends. Betelgeuse may not be ready to blow up just yet, but when it does, it will be a sight to behold. Until then, let's enjoy the twinkling stars. And remember, there's always something extraordinary happening in the vastness of space.
For the first time ever, we saw the shape of a supernova explosion in real time. The blast was so immensely powerful that it was literally ripping the surface of the star right in front of our eyes. Now we can finally understand what actually happens inside a star right before it blows apart. You see, massive stars fight against their own gravity their whole lives. They burn hotter and hotter elements to keep themselves from collapsing inward. But eventually, the star starts producing iron in its core. And this is a problem. Unlike many other elements, iron doesn't create energy inside the star. So once this process starts, the star loses its support system and gravity wins. The core collapses inward insanely fast, and then everything around it crashes down toward the center of the star. Once all that falling material slams into the dense core, it rebounds and creates a gigantic shockwave, and that's what rips the star apart. Scientists didn't fully understand how that part worked, but new observations helped them. They could watch the shockwave while it was actually moving through the outer layers of the star. Even better, they could see the shape of the explosion, and it wasn't what anyone expected. The blast wasn't perfectly round. It was slightly stretched in one direction. It may sound unimportant, but it can actually change how we understand supernovas and their final moments, when a star suddenly releases more energy than our sun will produce during its entire lifetime. The exploding star was first spotted on April 10, 2024, by a system called ATLAS, which scans the sky for dangerous or unusual objects. Just a few hours later, scientists already pointed one of the world's most powerful telescopes, the Very Large Telescope in Chile, directly at the discovery. For a very short time, the star's real shape and the shape of the explosion were both visible. But soon after, clouds of superheated gas hid everything. The star was a red supergiant. That's an enormous star close to the end of its life, about 12 to 15 times heavier than our sun. Normally, when we think of a supernova, we imagine a giant flash of light illuminating space. That flash happens when the shockwave from the collapse gets through the star's outer layers and releases a truly enormous amount of energy. For many months, the explosion shines brighter than whole galaxies, but the first few hours are the most important, and usually impossible to study because they pass super quickly. This time, scientists used a special technique that studies how light waves move and scatter. It helped them notice that the exploding material looked almost olive-shaped. Later, the explosion slammed into the gas surrounding the star and its shape flattened. But it still kept the same overall direction even while it was expanding outward into space. That detail may actually help us solve one of the biggest mysteries about supernovas. Right now, scientists have two main ideas about what can actually cause a giant dying star to explode. The first idea claims that tiny particles called neutrinos blast out from the collapsing star and heat everything around them, but the heating happens unevenly. So, the explosion becomes messy and unstable. That's why the star blows apart in a rough, uneven way. There's another theory. It sounds much more extreme. Some scientists think that the star sends out enormous streams of energy from deep inside its core right before exploding. These streams work like giant cosmic drills. They punch through the star and force the explosion outward in a more organized direction. The new supernova can tell us which idea is closer to the truth. The telescope data showed that the explosion had a very clear shape and direction almost from the very beginning. It didn't look random or chaotic. The blast stayed surprisingly symmetrical while it expanded through space. And that's a big clue. The explosion looked more like something fueled by powerful streams of energy rather than a messy neutrino blast. This discovery changes a lot. For decades, researchers have been arguing over what really happens inside a massive star during its final seconds. And now we can finally figure out the mechanism behind those gigantic explosions. And if you think that all supernovas happen insanely far away from Earth and don't affect us in the least, let me tell you this. Right now, Earth is drifting through the leftovers of a giant explosion that happened somewhere in space a very long time ago. And scientists just found some proof inside ancient Antarctic ice. Researchers were studying ice that had formed up to 80,000 years ago and discovered tiny traces of something called iron-60. You see, most iron on Earth is a normal version called iron-56, but iron-60 is different. It's radioactive, extremely rare, and it slowly disappears over millions of years. And it usually forms during supernovas. In simple terms, scientists found microscopic pieces of star ash frozen inside the ice. At first, researchers were confused. The Antarctic snow where they discovered this kind of iron was less than 20 years old. It made no sense. If a nearby star had exploded recently enough to spray this material onto Earth, we would have definitely noticed this. The sky would have lit up with one of the biggest cosmic explosions in history. But there was no supernova. This meant something else was going on. Eventually, they figured out the truth. Apparently, our entire solar system is currently moving through a gigantic cloud of gas and dust. Scientists call it the local interstellar cloud. For years, researchers suspected that this cloud may have formed after one or more huge stars exploded nearby a long time ago. And now, the discovery of iron-60 proves this idea. The material likely came from an ancient supernova that once sent its radioactive debris across space. Even after all this time, tiny particles from that explosion are still floating through our region of the galaxy, and some of them are literally falling onto Earth. To test the idea, scientists dug into old deep-sea sediments and ancient Antarctic ice cores going back 30,000, 40,000, and even 80,000 years. And every deeper layer gave them more evidence. The levels of iron-60 changed over time exactly the way they would have if Earth had been slowly drifting through a giant cloud filled with ancient supernova debris. And its microscopic radioactive particles have been falling on our planet for thousands of years. By the way, iron-60 was extremely difficult to find. Scientists started with around 660 pounds of Antarctic ice. After processing it, they started searching through trillions of atoms to spot just a few tiny traces of iron-60. But the search paid off. Researchers are sure that this ancient stellar debris may help us better understand the strange clouds surrounding our solar system. We can also learn more about the powerful cosmic events that had been affecting our galaxy before we even existed. Now, it might come as a surprise, but many of the elements you're made of come from supernovae. It can be anything, from the oxygen you breathe to the calcium in your bones. The iron in your blood or the silicon in your computer might have first appeared in the core of a star. And when a supernova exploded, it unleashed a storm of nuclear reactions, which in turn produced lots of building blocks making up the world around us. Supernovae are like giant particle machines in space. When a star explodes, the blast wave crashes into the gas around it and creates a super powerful magnetic storm. Tiny particles get trapped inside, bounce around, and speed up to insane speeds. Eventually, some of those particles shoot across space as cosmic rays. And then, some of them hit Earth. They slam into our atmosphere, smash into our atoms, and create invisible showers of particles that rain down on us all the time. Last summer, astronomers noticed something off, and it was, wait, that's not supposed to happen off. They spotted a weird mix of signals in their data. After double-checking, triple-checking, and probably staring at the screen in silence for a while, they realized it was something they'd never seen before. They may have just caught the first ever super kilonova. You've probably heard of supernovae, those big dramatic explosions marking the end of a star's life. It happens like this. A massive star runs out of fuel, its core collapses, and it blows itself apart. Sometimes a white dwarf star steals too much material from a nearby companion using its super powerful gravity. That stolen gas, mostly hydrogen, spins around the white dwarf in a disk and then slowly falls onto its surface, eventually triggering a massive thermonuclear blast. By the way, since we've mentioned it, a white dwarf is the scorching hot ultra-dense core that remains after a small or medium-sized star, like our Sun, exhausts its nuclear fuel and blows off its outer layers to form a planetary nebula. Then, over billions of years, it slowly cools and becomes a theoretical black dwarf. It's roughly the size of Earth but packs around the Sun's mass, which makes it incredibly dense. Black dwarfs are powered only by leftover heat, not ongoing fusion. Either way, the birth of a supernova is loud and bright. These explosions often leave behind a neutron star, which is so dense that a single teaspoon of it would weigh about 1 billion tons. Basically, less star and more cosmic anvil. But then there's this rarer kind of VIP event, the kilonova. Astronomers have only ever seen one of those. Back in 2017, one event confirmed what scientists had predicted for decades. 2 neutron stars slammed into each other and shook space-time with gravitational waves. Such collisions don't just look cool, they create heavy elements like gold and platinum. Kinda like a cosmic factory. There's a chance that the gold in your phone or on your finger was forged in a violent neutron star crash billions of years ago. Kilonovae have a signature look. The explosion produces so many heavy metals that they block blue light, leaving behind a deep red glow. It's subtle and incredibly hard to catch. Now, here's where things get interesting. What astronomers spotted in 2025 didn't really fit into the supernova box, but it didn't look like a regular kilonova either. It was too powerful and too strange. Neither did it behave the way either event should on its own. That's why some scientists believe they might have spotted something new, a super kilonova. We're talking about a collision or chain reaction so extreme that it goes beyond anything we've observed before. Right now, it's too early to draw conclusions. Astronomers are arguing politely, running more simulations, and waiting to see if the universe decides to do it again. Because in the universe, twice is often the proof. But how could this super kilonova occur? Scientists suggest quite a wild sequence of events. Picture this. A massive star collapses in a supernova, but instead of leaving behind one neutron star, it produces 2. Almost immediately, those 2 ultra-dense remnants begin spiraling toward each other. Within moments, they collide and merge, setting off a kilonova on top of the original explosion. In other words, it could be not just one cosmic blast, but a chain reaction. 2 of the most extreme events in the universe happening nearly back to back. The mystery itself started on August 18, 2025, when the LIGO and Virgo gravitational wave detectors picked up a signal from 1.3 billion light-years away. The event immediately caught attention. The ripples in space-time looked exactly like what astronomers would expect from two neutron stars crashing into each other. But there was a plot twist. The International LIGO Virgo Cagra team quickly alerted astronomers worldwide. The data suggested a neutron-star merger, but at least one of the objects seemed unusually small. Together, the pair weighed just 0.87 times the mass of the Sun. But neutron stars aren't supposed to be that light. According to everything we know, they should weigh at least 1.2 solar masses. At the same time, the analysis showed a 99% chance that one of the neutron stars fell below that limit. That shouldn't happen under normal conditions. So either the models were missing something, or this object formed in a completely different way. For example, it could be some kind of exotic birth during the collapse of a rapidly spinning, neutron-rich star. So, just a few hours after the alert, the Zwicky Transient Facility at Palomar Observatory spotted something curious. There was a fast-fading red glow coming from the same patch of sky. At first, it seemed that this discovery could solve the puzzle. For the first 3 days, the object behaved exactly like a kilonova. It glowed deep red, which is a sign of freshly forged heavy elements like gold and platinum. Everything matched: the timing, the color, and the gravitational waves. Astronomers thought they were witnessing the second confirmed kilonova ever seen. And that's where things got weird. On day 4, instead of fading away like a kilonova should, the object started getting brighter and bluer. That's like a major red flag in astronomy. Follow-up observations from the Keck Observatory in Hawaii revealed signatures of hydrogen and helium in the light, and those chemical fingerprints do not belong to kilonovae. They belong to supernovae, more specifically, a Type 2b stripped envelope supernova. This kind of explosion happens when a massive star loses most, but not all, of its hydrogen before blowing itself apart. It often happens because a nearby companion star siphons material away. At that point, many astronomers wrote the event off as a normal supernova that just accidentally happened near the gravitational wave signal. After all, regular supernovae don't usually produce detectable gravitational waves, but the timing and the early kilonova-like behavior, plus the strange mass measurements, didn't fit into that explanation. The event started to look like something far stranger. Now, most researchers still admit there's a chance all of this was just bad cosmic timing. Statistically speaking, they can't fully rule out that the neutron-star merger and the explosion just happened to occur near each other by coincidence. Still, the overlap in both time and location looked strange, and they couldn't ignore it. What if both signals came from the same catastrophic event? It would be an extreme scenario involving a rapidly spinning massive star. This star wouldn't collapse into a single dense core. Instead, its breakneck spin would cause the core to split in two, forming a pair of tiny underweight neutron stars. These newborn neutron stars wouldn't last long. Almost right after birth, they would spiral toward each other and collide. That crash would send out gravitational waves and create heavy elements, just like a normal kilonova. But all of this would happen inside a much larger supernova explosion. In other words, it would be a hybrid. One cosmic disaster stacked on top of another. Interestingly, the term superkilonova wasn't actually invented for this discovery. Originally, it described a theoretical event where a massive, fast-spinning star collapses straight into a black hole, surrounded by a huge disk of material. This material is capable of producing giant amounts of heavy elements, possibly several times the mass of the Sun in gold and platinum. The new study suggests using superkilonova to describe a supernova that briefly creates and destroys a pair of neutron stars before anyone notices what really happened. The team is careful not to oversell the idea. After all, the event happened far away. Moreover, the signals overlap in complicated ways, and untangling them perfectly isn't possible with current data. So, coincidence is still on the table. But if superkilonovae turn out to be real, they would help us solve several mysteries at once. For example, they offer a way to form low-mass neutron stars and help explain how the universe's heaviest elements might be created. Future observatories could help us figure out this phenomenon. Upcoming missions like NASA's Nancy Grace Roman Space Telescope and the UVEX satellite will watch the sky, increasing the chances of catching more of these blended explosions. If astronomers start detecting more mergers involving unusually small neutron stars, the case will finally be solved. Until then, the idea of a supernova and a kilonova happening together remains one of the most intriguing what-ifs in modern astronomy.
All the stars we see, including our Sun, are in a balance of powers. Stars are very heavy objects, so they have strong gravity, which presses them from the outside and makes them shrink. But inside a star, while it burns fuel, there are nuclear reactions that produce incredible amounts of energy. This energy is the light and heat that we feel during the day. But most importantly, these reactions increase the pressure inside the star and create a force that is fighting with gravity. So as long as the star has a full tank, it's safe. But then, the fuel runs out, the pressure inside the star falls, and the gravity wins. A star the size of our Sun can shine for about 10 billion years. Specifically, our lovely Sun is about 4.5 billion years old and has already burned half its fuel. The next stage in a star's life comes when it runs out of juice. Internal pressure drops, but gravity continues to press. At some point, a star simply collapses under its own weight and shrinks to the size of its core at the speed of almost a quarter of the speed of light. In less than half a second, a huge star turns into a small and dense object. This rapid collapse creates incredible shock waves that cause the upper layers of the star to explode. Now, an incredible amount of energy and matter is thrown into outer space. At this moment, luminosity of the star increases millions or even billions of times. This is the flash that our scientists can see with super powerful telescopes. But the light from this explosion doesn't reach our planet until many years later. So in fact, this star has long since faded. There are several options at this point. It all depends on the size of the star. If its mass is small, about the mass of our Sun, then for several months, this flash will become brighter and brighter until it reaches its peak. Then, the energy of the explosion will begin to dissipate, gradually fading and cooling down. A few years will pass, and the temperature of the former star will match that of space, and it will simply cease to exist. But the heavier the star, the more interesting the events will be. Heavy stars burn their fuel too quickly and have a much shorter lifespan. Stars weighing about 8 masses of the Sun can collapse into a rather unusual object, which is rarely found in the universe, a neutron star. This dull ball is only 6 to 12 miles wide and covered with a hard metal crust about half a mile thick. Neutron stars can weigh about 2 suns and have a strong gravity force. If you feel comfortable and in good shape on Earth, you wouldn't even be able to lift a needle or a match here. What's more, you would be pressed to the surface like a pancake and just unable to move. But there are stars dozens of times heavier than the Sun. An explosion of such a supernova, which weighs at least 40 times more than the Sun, gives birth to the most inexplicable and mysterious object in the universe, a black hole. At first, an incredibly bright explosion occurs. A shockwave spreads, carrying dust and matter of the former star around like a fog. And at the place of the explosion, only a small black disk is left. this black abyss is the heaviest object in the universe. It's so heavy that its gravity curves space-time around it. Yes, the closer you are to a black hole, the slower time will go for you. If you could get close enough to one of them, spend a couple of minutes in its orbit, and return to Earth, you would simply not recognize your home. 1 minute near a black hole can be a month, a year, or a decade on Earth. This depends on how heavy the black hole is. But don't get too close. The force of its gravity is so strong that even light can't escape from it. Humanity also knows about the existence of supermassive black holes. They gradually build up their mass, feeding on different cosmic objects just like a predator. Usually, such supermassive black holes lie in the centers of galaxies, and their gravity is so strong they can hold countless stars near them. For example, this is the only photo of a black hole, which is located in the center of the Messier 87 galaxy. The orange glow around it is its event horizon. That's the remains of the light from the objects this black hole has swallowed. You're quite safe though. The closest black hole is 1,120 light-years away. But supernovae can explode not only when gravity wins the fight with the star's internal forces. Sometimes the opposite happens. The nuclear fusion inside the star begins to affect much more matter than normal. The pressure inside a star increases, and it defeats the force of gravity that exerts pressure on the star from outside. At this point, there's a boom! This never happens by itself, and this type of supernova is only possible in binary star systems. Two stars are spinning around each other. One star begins to swallow the substance from the other. Then, the nuclear reactions inside it are no longer in balance, and a supernova explodes. For some time, scientists believed that such an explosion could occur in 2022. There's such a binary system in the Swan constellation at a distance of 1,800 light-years from the Sun. The luminous red nova should have occurred here. Such a red flash would have been visible to the naked eye for months. And after the explosion itself and the merger of two stars, a new, hotter, and heavier star was to appear in their place. But a new analysis of the data revealed a calculation error, and this event will not happen soon after all. So now we see that a supernova explosion is a very dangerous event, and it can cause great harm to our planet if it happens close enough. The main danger is gamma rays. This is the radiation that comes from the explosion. When these rays reach the Earth, they affect our space shield, the atmosphere. They reduce the ozone layer and make us vulnerable to solar radiation and cosmic rays. In this case, all life on the planet is in incredible danger. And the bad news is that such an explosion could happen quite soon. Betelgeuse, the brightest star in the night sky, about 17 times larger than the Sun and 8.5 billion years old. It's begun to exhaust its fuel reserves. Scientists predict that this giant will explode like a supernova at any moment within the next 10,000 years. So it may happen in a few centuries or even tomorrow. Everything will happen as follows. Betelgeuse will collapse in a fraction of a second, and then it will explode so brightly that it will look like a second moon in the night sky. We will observe a new bright spot in the sky for weeks or even months. But then, it will begin to fade until it completely disappears. Not without a trace though. In its place, there will be a neutron star, weighing 1.5 times the Sun. It will be one of the biggest events that humanity has ever seen. Still, we have nothing to be afraid of. Betelgeuse is about 550 light-years away from us, so its X-rays and ultraviolet light will not affect us. A much greater danger is posed by the release of material that occurs in a supernova explosion. But this shouldn't make you worried either. The shock wave won't reach the Earth until 6 million years later, and it will be suppressed by the oncoming solar wind. So if we see Betelgeuse explode today, it will be an epic sight. But in fact, the star will not exist at the time because it will mean the event itself happened almost 6 centuries ago. It's just that now the light from it has reached us. Some scientists believe that the Ordovician Silurian extinction events, which occurred almost 500 million years ago, happened exactly because of a star explosion. Then, almost 60% of marine vertebrates went extinct. Yet, it was not a supernova, but a hypernova. That is what scientists call explosions of stars 100 to 150 times larger than the Sun. In addition to the abnormal weight, the star must rotate very quickly. Such objects are very rare. In our galaxy, there are few of them, and scientists believe that hypernovae occur about once in 200 million years.
A powerful solar storm can mess up life on Earth in a catastrophic way. It can leave huge regions of our planet without power, disrupt communication and navigation satellites, damage power grids and data centers. Scientists warn that the next major solar storm could become one of the most devastating natural disasters. And the question isn't if it happens. The correct question is when. And the scary part? This kind of weather doesn't happen in Earth's atmosphere at all. It starts 93 million miles away on the Sun. When the Sun becomes active, we can feel it on Earth. This activity can mess with satellites, GPS, radio signals, and even parts of the power grid. Scientists usually group space weather into 3 main types: radio blackouts, geomagnetic storms, and radiation storms from the Sun. Each one has a different effect on Earth. Radio blackouts happen when the Sun sends a powerful burst of energy, aka a solar flare, our way. When that energy reaches Earth, it hits the upper atmosphere and disrupts the way radio signals travel. Geomagnetic storms are different. Sometimes the Sun launches enormous clouds of superheated gas into space. These eruptions are called coronal mass ejections. Imagine billions of tons of solar material blasted away from the Sun at a speed of millions of miles per hour. If one of those clouds comes across Earth, it slams into our planet's magnetic field at full speed. The result is a massive geomagnetic storm. We've already seen some serious space weather recently. For example, in May 2024, the strongest space weather event since 2003 hit Earth. GPS systems went through massive disruptions. The US agricultural industry was hit hard, all because modern farming needs satellite navigation to work properly. As for the infamous 2003 event, it completely cut power in parts of Sweden and South Africa. You might be wondering, what will happen if we get something even bigger? Scientists decided to figure out what a true worst-case space weather event might look like. Now, worst case doesn't mean a once-in-a-million-year disaster. Planning for something that rare isn't super useful. Instead, researchers focused on events that could realistically happen once every 100 to 200 years. Rare, but not impossible. When a strong geomagnetic storm hits Earth, it doesn't just affect space. It can actually generate electric currents in the ground too. And since power lines are excellent conductors, those currents can get inside the electrical grid. It's like extra electricity getting suddenly injected into a system that wasn't designed to deal with it. If the currents are strong enough, they can overload parts of the grid. Safety systems may automatically shut sections down to prevent damage, potentially leading to massive blackouts. Whole regions might stay without electricity. But losing power isn't even the worst part. The extra current can also damage transformers, those massive machines that help move electricity across the grid. Some of these transformers weigh hundreds of tons and can take months or even years to replace. This means that even after the storm is over, parts of the electrical network may still remain damaged for a long time. The power grid on Earth isn't the only thing at risk. A serious space weather event will first mess with satellites hundreds of miles above our heads. And we depend on satellites far more than most people realize. They help us navigate, forecast the weather, communicate with relatives and friends all over the world, and track ships and aircraft. During a bad solar storm, many of those satellites could run into serious trouble. One problem is radiation. When the sun throws large amounts of energetic particles into space, those particles can slam directly into spacecraft. Over time, they can damage electronics and slowly wear down solar panels, shortening a satellite's lifespan. During an especially powerful event, some satellites could fail completely. But there's another huge problem. A solar flare can actually heat Earth's upper atmosphere. When that happens, the atmosphere expands outward and becomes slightly thicker at altitudes where many satellites orbit. The change is tiny, but for satellites, it matters a lot. Imagine riding a bike on a smooth road, and then suddenly someone pours a thin layer of mud over it. You can still move forward, but you'll slow down faster than before. Something similar happens to satellites. The thicker atmosphere creates extra drag, and that drag slowly pulls satellites into lower orbits. If they lose too much altitude, some spacecraft can fall back into the atmosphere and burn up. And it's happened before. In 2022, solar activity caused Earth's atmosphere to expand right after a batch of Starlink satellites was launched. Around 40 of them couldn't maintain their orbits and eventually re-entered the atmosphere. But during a real worst-case solar storm, the situation could become way more dramatic. It could also prevent us from tracking satellites and increase the risk of their collisions with space debris. The next problem is radio signals. Right now, they're constantly passing through the air around you. Your phone, GPS, Wi-Fi, aircraft communications, ship navigation systems, emergency services, all of them depend on radio waves. And a bad solar storm can mess up many of those signals. Solar flares produce bursts of radio energy, and sometimes those bursts become so powerful that they drown out weaker signals on Earth. It's kinda like trying to hear someone whisper while a jet engine is running nearby. None of this means that a giant solar storm would send us back to the Stone Age. Even a worst-case event probably wouldn't be a Hollywood-style apocalypse. But it could create a chain reaction of problems. Satellites could fail. GPS could become unreliable. Flights could be canceled. And parts of the power grid could be damaged. That's exactly why scientists spend so much time studying space weather. And now, they might have to come up with a pretty cool idea for protecting Earth from powerful solar storms. They proposed something called Storm Wall. The idea is simple. What if we don't just wait for solar storms to hit and deal with the damage? What if we weaken the solar storm before it reaches Earth? The idea is based on Earth's magnetic field. Our planet is surrounded by a giant magnetic bubble called the magnetosphere. It's like an invisible shield that helps protect us from charged particles coming from the sun. Researchers noticed that Earth's atmosphere already helps strengthen this shield. Tiny particles escape from the atmosphere and interact with the outer edge of the magnetosphere. So scientists decided to try to boost that process on purpose. Their plan involves 6 spacecraft orbiting Earth. Each spacecraft would carry materials like barium or lithium. If you release them into space, sunlight would charge those materials, turning them into a cloud of plasma. Plasma is basically a gas whose particles carry electric charges. The sun itself is mostly made of plasma. The idea is that those artificial plasma clouds would form near the edge of Earth's magnetic shield, and when a solar storm arrived, the plasma would help absorb, redirect, and weaken some of the storm's energy before it reaches Earth. According to the team's simulations, the system could reduce the strength of a serious geomagnetic storm by 50%. That would be a really great result. A storm that's cut in half would mean less damage to satellites, fewer communication problems, fewer GPS disruptions, and less stress on power grids. Of course, this is still just a concept. Nobody has built the storm wall yet. Nobody even knows for sure whether it would work exactly as planned in the real world, but the researchers say that the physics behind it checks out. And apparently, modern rockets can indeed launch the equipment we'd need for such a mission. There's just one problem, and it's money. Building and launching 6 spacecraft wouldn't be cheap. Plus, once the material is released into space, it's gone. You can't collect it, refill it, or use it again. The researchers believe that the mission would use about as much material as a dozen large tanker trucks. That's why the price of a truly massive solar storm could be exorbitant. A solar storm is crashing into Earth like a cosmic tsunami. First, the atmosphere ignites, sparking massive auroras. High-energy radiation slams into the surface, frying power grids, turning lights off across continents, and knocking out satellites. Planes lose navigation, radios go silent, GPS systems crash, radiation levels spike dangerously. Communication collapses, emergency services scramble in the darkness, and chaos spreads as people struggle to cope. Solar particles start to strip away the very air we breathe, slowly peeling off our atmosphere. Soon, Earth will become a harsh and hostile place. That's what solar activity can do to our planet and its inhabitants if we didn't have a protective shield called the magnetosphere. But even with this barrier, we're still in for serious problems. A mysterious 100-year solar cycle may have just restarted, and it could mean decades of dangerous space weather. New research suggests that the unexpected intensity of the ongoing solar maximum may be partly tied to a lesser-known 100-year solar cycle. If the Sun is indeed entering its villain arc, solar activity could spike even further in the coming decades. It means more solar flares, more chances of them messing with satellites, and way more of those crazy northern lights people keep posting on Instagram. Sure, not everyone's buying it. Some space nerds want more proof before jumping on this solar hype train. Let's break it all down into detail first. The Sun goes through a kind of mood swing every 11 years. This is called the solar cycle. It starts off at a solar minimum, which is pretty chill, then slowly gets rowdy. We're talking sunspots, solar flares, and other fiery drama. Once we reach solar maximum, the situation starts to calm down again. The Sun gets sunspots, dark patches on its surface, like the freckles we humans have, when its magnetic field starts flipping out. Literally, the Sun's magnetic field completely flips during peak solar drama. Scientists track how many of these spots show up to measure how spicy the Sun is getting. But wait, plot twist, there are other cycles too, like the Hale cycle, which occurs around every 22 years. This cycle controls how magnetic fields move across the Sun. Plus, way back in history, there were moments when the Sun basically went on Do Not Disturb mode. During the Maunder minimum, our star was basically in sleep mode for 70 years. In other words, the Sun might be entering a new extra phase, and things could get dramatic. On the bright side, that means more auroras. At the same time, it could also cause issues for satellites, GPS, and other stuff we rely on. Ugh, let's just hope it doesn't mess with YouTube. This extra phase is called the Centennial Gleisberg cycle. It's basically the Sun's once every 100 years I do something weird moment. Scientists think it messes with how intense sunspot cycles get. No one has fully worked out how this cycle works yet, but some low-key sloshing of magnetic fields inside the Sun might be causing it. Yep, I did say sloshing, like a giant cosmic smoothie. A recent study from March 2025 claims that the CGC might have just hit restart. That could explain why this current solar maximum, the Sun's drama phase that started in early 2024, is being so weird and unpredictable. How did researchers figure this out? They looked at something called proton flux. Basically, it's how many positively charged particles are flying around in Earth's radiation belt. There are 2 of these belts, shaped like donuts that wrap around Earth, full of particles from the sun. The thing is, when the sun is active, our upper atmosphere swells, which makes the inner radiation belt lose some of those protons. And when the sun is chill, proton numbers go up again. So those protons have been increasing for like 20 years, but just started to drop in the past year. Which basically screams CGC has just hit minimum. Time for the sun to crank it back up. The data came from NOAA satellites that flew through the South Atlantic anomaly, which is like the Bermuda Triangle of space. It's this bizarre zone over South America where Earth's magnetic field is weaker and space radiation gets closer to Earth. This area is perfect for observing proton activity without sending a satellite into the actual danger zone. So, right now, we're probably nearing the end of the sun's current chaos phase, aka the peak of solar cycle 25. Back in May 2024, it hit us with one of the craziest geomagnetic storms in 500 years or so. And yes, that means super bright auroras lighting up skies all over the world, even in places that usually only get clouds and vibes. But the scariest thing? This wasn't supposed to happen. During the last cycle, the sun was oddly calm. So NASA and NOAA looked at that and thought that the next solar cycle would probably be the same. No biggie. Well, they were wrong. And they even admitted it. Now, scientists think that SC24's quiet phase was because of the Centennial Gleisberg cycle being at its low point. That probably made it the quietest sunspot cycle in 100 years. So now that SC25 is lit again, pretty literally, it might just mean the sun is back to doing what it normally does, being a little chaotic and wild. Recent studies think the CGC minimum is finally over. That would explain why the current solar activity is turning up the heat, and why the last one felt like a cosmic snooze. An even cooler thing is that a 2024 study used AI to analyze sunspot patterns and found that CGC might be messing with our forecasts more than we thought. And if this long-term mood swing of our star is really back on the rise, future solar cycles could be just as wild as the one we're in now, or even wilder. After all, we've just passed the CGC's low-energy mode, and we won't hit the next maximum for another 40 to 50 years, around solar cycle 28. That's a few decades away, but the sun's already throwing tantrums. The scariest part is that future solar activity might be twice as intense as what we're seeing now. You might be wondering right now, why should I care? Well, because when the sun freaks out, it messes with our stuff, especially in space. Satellites get dragged out of orbit because Earth's upper atmosphere literally puffs up like a marshmallow in a microwave when solar activity spikes. And this has already happened to a few spacecraft recently. And with tons of private satellite mega constellations like Starlink and its squad, the risk goes way up. There are some, even though those are few, that might not be ready for a full-blown sun rage event. Time to wear SPF 100 for your satellites. Astronauts are also at risk. More solar flares mean more radiation and more danger for humans in orbit. At the same time, more space tourists and missions mean more people potentially in the sun's cosmic splash zone. At the same time, not everyone is buying into the whole CGC is back and ready to party theory. Some experts say it's a cool theory, but we shouldn't get carried away. The thing is, the proton flux, those space particles we've been watching, only started dropping last year. That's not a lot of time. It might just be a short-term dip, like the sun sneezed and now everyone's freaking out. Also, we've only been able to track this stuff properly for 30 to 40 years or so, which is basically nothing in sun time. So there's no solid before and after data to compare CGC cycles and say, yep, this is definitely a pattern. Plus, the CGC itself is kinda mysterious. Like no one can fully agree on what it even is, how it works, or how much it actually messes with sunspot cycles. It's like the Bigfoot of solar science, blurry, weird, and causing drama in group chats. But even skeptics admit that the new study is interesting and well-intentioned, and that it might help us predict future solar cycles better. We just need more time, more data, and better definition of the CGC before we treat it like the ultimate weather app for the sun. In May 2024, stunning auroras adorning the night sky demonstrated all the power that solar storms emit as radiation. But sometimes, our sun does things that are far more destructive. I'm talking about solar particle events. During these events, blasts of protons coming directly from the surface of the sun can shoot out like giant cosmic searchlights. According to records, an extreme particle event hits Earth every 1,000 years or so. It often causes bad damage to the ozone layer and increases levels of ultraviolet radiation closer to the surface of our planet. Luckily, Earth's magnetic field acts as a powerful protective cocoon for our planet, fending off electrically charged radiation from the sun. In its normal state, this field functions like a ginormous bar magnet, with field lines rising from one pole, looping around the planet, and dropping at the other pole. This pattern is sometimes called an inverted grapefruit. This vertical orientation of the magnetic field at the poles allows some ionizing cosmic radiation to get through the field as far down as the upper atmosphere. There, it interacts with gas molecules and produces the glow we know as auroras. But over time, Earth's protective bubble changes. In the past century, the North Magnetic Pole moved across northern Canada at a speed of about 25 miles per year. Plus, it weakened by more than 6%. Even more shockingly, according to geological records, there have been periods of time as long as centuries and millennia when our planet's magnetic field was super weak or entirely absent. But we'll talk about those tragic times later. It's easy to imagine what our planet would look like without its protective bubble if you look at Mars. The red planet lost its global magnetic field long ago. And once this field disappeared, most of Mars's atmosphere vanished too. In May 2024, a strong solar particle event hit the planet. It disrupted the operation of the Mars Odyssey spacecraft and made radiation levels at the surface of the red planet rise around 30 times higher than what a person receives during a chest X-ray. The sun's outer atmosphere constantly emits a changing stream of electrons and protons, the solar wind. At the same time, the surface of the star also produces bursts of energy, mostly protons, during solar particle events. These bursts of energy have a connection to solar flares, extremely powerful bursts of electromagnetic radiation that can last from minutes to hours. Protons are way heavier than electrons and carry more energy. That's why they can reach lower levels of Earth's atmosphere, exciting gas molecules in the air. These excited molecules emit X-rays invisible to the unaided eye. Dozens and hundreds of relatively weak solar particle events happen during every solar cycle. Now, let's speak about solar cycles for a minute. You see, from a distance, the sun seems to be calm and steady, but if you zoom in, you'll see that its surface is constantly seething and churning. It keeps transforming from a uniform ocean of fire to a chaos of warped plasma and back again in a repeating cycle. Every 11 years or so, the magnetic field of our star gets tangled up. Imagine a ball of tightly wound rubber bands. That's what it looks like at such moments. And then, at one point, it snaps and flips completely, turning the North Pole into the South Pole, and vice versa. Right before this event, the sun steps up its activity. It starts to spit out giant blobs of fiery plasma, emit powerful streams of radiation, and grow planet-sized spots. This period has the name of solar maximum. It's a rather dangerous time for Earth, since it gets regularly hit by solar storms. Such storms have the potential to disrupt communications and damage power infrastructure. Even worse, solar storms can harm astronauts working in space and even make satellites crash into the planet. As the cycle ends, it fades back to the solar minimum, and then a new cycle begins. Anyway, back to our solar particle events. Researchers have found traces of extremely strong solar events happening throughout the history of Earth. And some of them were thousands of times stronger than anything our modern instruments have ever recorded. Such extreme solar particle events happen approximately every few millennia. The most recent one occurred around 993 CE. Beyond the immediate effect they have, solar particle events can kickstart a chain of chemical reactions in the upper atmosphere. And these processes often lead to depletion of ozone, which isn't a good thing. Ozone absorbs harmful solar UV radiation, which can damage not only our eyesight, but also the DNA of living beings. Plus, changing the amounts of ozone in the atmosphere can impact the climate. In a recent study, researchers used large computer models to examine how extreme solar particle events affect Earth. They found out that if a solar proton event arrives during a period of time when our planet's magnetic field is very weak, then ozone damage can last for 6 years, and the level of UV radiation might increase by 25%, boosting solar-induced DNA damage by around 50%. And apparently, this dramatic combination of a weak magnetic field and extreme solar proton events happens quite often. And some researchers believe that it may even explain a few mysterious occurrences in the past of our planet. For example, the most recent period of weak magnetic field started 42,000 years ago and lasted for around 1,000 years. This period included a temporary switch in the North and South poles. Several major evolutionary events happened during that time. For example, the last Neanderthals disappeared in Europe, along with the extinction of marsupial megafauna in Australia. Yeah, sadly, we won't see any giant wombats and giant kangaroos anymore. One more, even bigger evolutionary event might also be linked to Earth's geomagnetic field. Multicellular animals appeared at the end of the Ediacaran period, which started around 635 million years ago, and it occurred after a 26 million year period of extremely weak or even absent magnetic field. The rapid evolution of different groups of animals in the Cambrian explosion, about 539 million years ago, might have also been related to high UV levels and geomagnetism. The simultaneous evolution of hard body shells and eyes in multiple unrelated groups could have been necessary to detect and avoid harmful incoming UV rays. A complete reversal of Earth's geomagnetic poles might have a serious impact on the climate of our planet. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. That's why the magnetosphere continues protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Our planet's magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current's negative charge, called electrons, move through the metal. The current is what generates a magnetic field. Earth's outer core is made of liquid iron and nickel. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving throughout the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic ray radiation, which otherwise would be extremely hazardous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal poor star. It suggests that the star that collapsed and formed BH3 was metal poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course, the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.